I think what I'm going to do now is I'm going to, instead of going directly to the where we left off in the Bessel function chapter, I'm going to go to the integral equation chapter and repeat, maybe at a quicker pace, what I said yesterday in the problem session, and then go on a little bit further and show you how the Hankel functions can be defined. And actually, there is something quite interesting about the in the integral equation chapter. It's just not normally covered in books like this, so that's the reason why I skipped it when I thought we didn't have enough time. So the basic idea is, suppose you have an equation u prime is pu plus q. That's a differential equation, and what you can do is you can convert it to an integral equation. U of x is integral a to x pu dy plus integral a to x q dy plus u of a. So that's very easy. If you do that twice and work a little bit harder, you can take the differential equation u double prime is pu prime plus qu plus r, and you turn it into u of x, let us say, equals f of x plus an integral from a to x of a kernel k of x and y, u of y dy, where the kernel k, this is not kernel standards, k of x and y is equal to p of y plus x minus y times q of y minus p prime of y. And f is a little bit more complicated. F of x is a constant u of a plus x minus a u prime of a minus p of a u of a plus an integral from a to x of x minus y r of y dy. And I presume that this can be generalized, that you can have an n-order differential equation, you can convert it to a system of integral equations. There are two reasons why one might want to do this. The first is that once you have your solution expressed as an integral, you then have more control over it mathematically, because integrals are intrinsically smoothing operations. The second reason is that there are remarkable tricks that we'll get to at the end of the lecture that you can do with integral equations that are not apparent if you just have a differential equation. And we'll get to them, as I said, at the end of the lecture. Now, let me say, if we have plenty of time, there is a sign-in sheet floating around somewhere. If we have time at the end of the lecture, I'll come down and derive these expressions. I'm not sure how time is going to go in this lecture.
Can I ask a question?
Absolutely, and I have to pay the TA. Good catch.
So I'm confused why so in the second line, you integrate in terms of dy.
Yeah.
U is a function of x.
Yeah, everything up here is a function of x. And now we're writing u of x as p of, the integral p of y, u of y dy, plus q of y dy, plus u of a, u and a.
Is that different from doing a indefinite integral and integrating in terms of dx with a constant? I guess I'm just wondering why we do it with from a to x in terms of dy instead of dx.
Suppose you were going to get really serious mathematically. Then an indefinite integral isn't terribly useful. Instead, you can think about these things as, you know, you could think of them in terms of a Riemann integral, or better yet, a Lebesgue integral, and then you can do things mathematically that you can't just do with an indefinite integral.
Okay.
So you have more control mathematically, and as I say, we'll get to something in the end of the hour that's kind of interesting. So I'm wondering, maybe I should leave these boards blank because we might come back and derive these. The first part is obvious. Obviously, you take this thing and integrate it and you get that. The one that requires a little derivation is the second one. So let me, oh hell, why don't I just do the derivation? I haven't looked at it in quite a while, but let's just see what you can do. Well, the first thing is you take this differential equation and you integrate once, and you get u prime of x is an integral from a to x of p u prime plus q u plus r, all of these as functions of y, dy plus u prime of a. So that's one integration. Now you have to integrate and use a trick. And let me show you the trick. The trick is equation 7.58, which wasn't good gracious. Right. Oh, that's interesting. This trick is the baby version of what you were talking about on Wednesday. So let me show you this trick. This is a nice trick. I'm glad I decided to derive this because the trick is really worth knowing. So let me do the trick up here. Integral from a to x dz. Integral from a to z dy of f of y is equal to an integral a to x of x minus y f of y dy. So in other words, a double integral, which is what we're going to encounter if we integrate this equation a second time, a double integral is equivalent to a single integral, but with a kernel. Is that a question back there?
No. Right? I guess it is a question.
Mr. Candy Store question, yes.
So if you integrate by parts to show this, wouldn't you get an extra boundary term?
Well, all right. Let's.
Don't you get a,
All right. Let me give you then the derivation of this. I brought the solutions with me.
oh wait,
today.
never mind. I see what you have.
Okay, so let me derive this.
Yeah.
We differentiate with respect to x, and what we get is integral a to x dy f of y is equal to, now if we differentiate with respect to x, we get integral I'm sorry, we don't get that. We get, let me get this straight. Differentiating with respect to x, we get this thing here with y set equal to x, right? So that would give us 0. If we differentiate with respect to this guy, on the other hand, what we get is integral a to x f of y dy. So that's obviously a true equation. So this thing can be off by at most a constant. And if we now set x equal to a, we see the constant would have to be 0.
Confused. You just wrote the same
And
thing.
all right, let me just remind you of, I'm sorry, what?
Well, we're saying you just wrote the same thing.
You
You
just
wrote the
wrote
same
the
equation
same
equals the
thing
same
on both
equation.
sides of the.
Hey, you flipped it.
No, but wait.
Yeah, you just wrote the same
Maybe of
Let's
that. And this is obviously true. Okay. So this thing, so both sides of this equation have the same derivative. Therefore, at
Oh, I
most
see,
you
I
can
see,
have
okay.
this equals that plus a constant. Now you set x equal to a, and the constant becomes 0.
Okay.
And there's a much more general form of this, and Austin told me yesterday this is actually due to Cauchy, or Cauchy, if you pronounce it in a semi-French way. All right, so now I've a little lost track what we do. Yes, okay, if we then use this trick and integrate again, what we get is u of x is integral a to x dz, integral a to z dy, and then it's this whole thing here, which is pu prime plus qu plus r plus u prime of a plus u of a. That's what we get. And now, using this trick on that, what we get is that this is equal to integral a to x dy, x minus y, pu prime plus qu plus r, plus x minus a, u prime of a, plus u of a. So these guys are all evaluated as y. Well, this basically is the answer here. So I don't think, you just sort of decompose this and you get that. So I don't think we need to go any further with this. So getting back to the basic discussion here. Okay. Getting back to the basic discussion here, then we go to, so we've seen how basically you can take differential equations, turn them into integral equations. Now, the basic idea is here, if we have an integral a to b, k of x and y, u of y dy equals lambda u of x plus f of x, then this is called an inhomogeneous Fredholm equation of the second kind. So this is inhomogeneous Fredholm 2. Okay. Now, if we do the same thing but set f equal to 0, we obviously get ab k of x y u of y y equals lambda u of x. Notice here, this is the inhomogeneous term. Lambda is an eigenvalue. Since you've got u on both sides, u is the eigenfunction. You can multiply that by an arbitrary complex number, and it'll still be a solution as long as you have the homogeneous case. And so this one here is called homogeneous Fredholm 2. So on the other hand, you set lambda equal to 0, then what you have is, so for lambda equals 0, you have inhomogeneous Fredholm 1, and here lambda equals 0, you have homogeneous Fredholm 1. Okay. So these are the definitions of the various kinds of integral equations. And the Fredholm equations are the general equations. The Volterra equations are just a special case. So Volterra is if k of x and y is causal. That is to say, if it is equal to k of x and y times theta of x minus y. Well, what this says then is that y contributes to x only if y is lower than x. And so this is causal. Volterra. Okay. Okay, now because these equations are linear, you're basically home free. Linear differential and integral equations can always be, you can always basically solve them one way or another. By the way, just to remind you about the final exam, it's Thursday of next week, open book. We discussed, before some of you came in, we discussed whether it should be open laptop or open MATLAB, and what we decided was that some people who have electronic copies of the book can bring a laptop or something, but they're not supposed to use MATLAB, Mathematica, or their friends through the by using the laptop. So, are you all comfortable with that?
Sure.
And as I said on Wednesday, you should study for the final and do your homework in order to learn mathematics to do physics or whatever else you're going to do later in life. Don't study for the exam in order to get a good grade. Just study in order to learn. Make that your focus. One of my sons, by the way, I think I've told you this, but I'll repeat it. He's in the software industry, and he said that anybody who knows mathematics and Python can get a very good job these days. And Python, of course, is free, and any of you can teach yourself Python in a couple of weeks. Okay, so you could all put on your resume that you're a Python expert and a math expert. And then if you do get a job offer, learn Python really fast. And you're in like Flynn. Okay, so what are the implications of linearity? Let's first look at the equation k of x and y. K is called the kernel, as I've said. uj of y dy is equal to lambda uj of x. So this is a homogeneous Fredholm equation of the second kind. And if uj is a solution for various j's with the same eigenvalue, then what you can do is you can just add the solutions together and you'll have k of x and y. Sum aj, uj of y, dy will equal lambda sum aj, uj of x. Okay, so this is just like for differential equations. And what about the difference of any two solutions? Well, or first of all, let's suppose that we have a solution of the inhomogeneous equation. So we have something that's k of x and y, u inhomogeneous, and I'll just call it ui of y, dy is equal to lambda u inhomogeneous of x plus f of x. So now this is an inhomogeneous Fredholm equation of the second kind, and we have ui as a solution. And then, actually I do need to put an index. I'll put an index k here. So suppose you have several solutions of the inhomogeneous equation. Then a to b k of x and y, the difference of two solutions of the inhomogeneous equation will be a solution of the homogeneous Fredholm equation of the second kind, the same one. And so that tells us that the difference of the two is a solution of the homogeneous equation. The most general solution of the homogeneous equation is a linear combination of all the solutions of the homogeneous equation. And consequently, you can write ui of k, ui sub k is, in other words, ui k of x then is ui k prime of x plus something homogeneous, so that's a sum aj, uj of x. And this tells you then the most general solution of the inhomogeneous Fredholm equation of the second kind is a particular solution of the inhomogeneous plus the general solution of the homogeneous, which is an echo of what we learned with differential equations. Okay, now let's go to numerical solutions. And here, because the equation is linear, linear algebra applies, and so one can one can basically use MATLAB or LAPAC, which are Fortran programs that are parallelizable, or you can use C++ programs or C programs, I forget which, in NIST libraries. And so what you do then, first of all, for the homogeneous Fredholm equation of the second kind, what you do is we're looking at a to b, k of x and y, y dy, we want that to be lambda u of x. So what we do, and we have here x less than or equal to b, greater than or equal to a, we divide this interval into a set of smaller intervals, and we basically say that delta y is equal to b minus a divided by n, and you can take n to be 100 or a million, whatever you want to do. These days it really doesn't matter. We set y0 equal to a. Yk is then a plus k delta y, y sub n is equal to b, and then we define a vector u, and the kth entry of the vector is u of yk, and then we define a matrix k sub, let us say ij, and that's the kernel at xi yj times delta y. And now this homogeneous Fredholm equation of the second kind from an eigenvalue lambda becomes a matrix equation, a sum on j equals 0 to n, kij uj is equal to lambda ui. In matrix notation, that's just ku equals lambda u. And we learned in section 26 of chapter 1 that these things have solutions. There's a u that does this if and only if the determinant of k minus lambda times the identity, n by n identity, equals 0. If there is such a solution, if the determinant, well, what you do is you then solve, you ask your computer to solve this equation. Now, I was saying that this was trivial until I realized that at this step, it's not exactly trivial, because this is a characteristic equation, and if you have 1,000 points, it's a degree of 1,000. I imagine there are programs that solve that. It's not that, it's not hopeless. Anyway, that gives you then eigenvectors or eigenvalues lambda alpha, and in fact, potentially you'd have many, a great many eigenvalues, but because an equation that's this, a matrix that big could have, if it's 1,000 by 1,000, it could have in principle 1,000 eigenvalues. But anyway, you find whatever they are, and then that gives you the eigenvalues, and then then you can find the eigenvectors such that k minus lambda I u is equal to 0. For the inhomogeneous case, well, by the way, the fact that there are a large number of eigenvalues shouldn't bother us, because remember, if we have a self-adjoint differential system, then if the eigenvalues go to infinity, then the eigenfunctions form a complete set. And so that's kind of what we would want. Okay, so that's that. If we now apply this to, let us say, an inhomogeneous Fredholm equation of the first kind, then we have a to b, k of x of y, u of y dy is equal to f of x. Well, now using the same discretization of the problem, what we have is k u is equal to the vector f, which is just a function f at these 1,000 points, whatever. In other words, f sub k is equal to f of x. And if the determinant of k is not equal to 0, which is to say if it doesn't have any zero eigenvalues, or if the analogous equation didn't have any zero eigenvalues, then what you do is you write U is equal to K inverse F, because the determinant is non-zero, so this is determinant. Then K has an inverse, and you write your solution as K inverse F. So now if we apply it to an inhomogeneous Fredholm equation of the second kind, in other words, if we have, let me just take this equation and just add the eigenvalue term, then what we have now is Ku is equal to lambda U plus F. And now the homogeneous equation, of course, is Ku equals lambda U. You find the most general solution of it, and then you pick a lambda that's not one of the eigenvalues. So you have a zillion eigenvalues. You pick a lambda that's not one of the eigenvalues. And then you look for something, an inhomogeneous solution, such that Ku is U inhomogeneous is Ui plus F. And now that matrix equation is K minus lambda I on U inhomogeneous is equal to F. If lambda is not an eigenvalue, the determinant of this doesn't vanish. This thing has an inverse, and you write U inhomogeneous is K minus lambda I inverse acting on F. And then you add to this solution the most general solution of the homogeneous equations. There's a little more about this discrete technique, but I think it's a little bit technical, so I'm going to skip it and go to the next topic, which is the one that I promised you, and I've been going through this much faster than I thought I would. The next topic is what we might say, what I think is an unexpected advantage of transforming a differential equation into an integral equation. And the idea is integral transformations. And this concept is what's behind Fourier and Laplace transforms and other kinds of transforms. And if you want to read about these, you might look at Courant and Hilbert. Hilbert of Hilbert Space and Courant of the Courant Institute at NYU, Lower Manhattan. Chapter 7. Anyway, so we have, let us say we have a differential equation of this form. L is a differential operator and C is a constant. Now, it turns out, well, I mean, just think about it. All the functions that we know about are nice functions. We don't like unnice functions. And so the functions the useful functions are essentially analytic. I mean, they might have singularities, and they typically do have singularities somewhere, but they're typically analytic. So what we're going to do is we're going to generalize this to linear differential operators that involve derivatives with respect to a complex parameter, and U is a function of Z. So this will be L sub Z, meaning differentiate with respect to Z, plus C, U of Z is 0. So that's kind of what we're thinking. Now, the trick here is to try a solution, look for a solution of this form. U of z is integral, and you know if you're doing complex variable theory, you're going to use a contour integral. Here's a contour integral. And the trick is to pick a kernel, which I'm writing as capital Z and W, V of W, dW. So in other words, we're doing two things here. The first is that we're going to pick a K, a kernel that's relevant and helpful, and then look for a solution V. And here's the big trick. The big trick is that if you pick the right kernel, you can find V very easily. Whereas, as you know from your experience with Bessel functions, the formulas for U, at least for the cylindrical Bessel functions, in general are quite complicated. So here, whereas if in the differential equation point of view, you have to use the method of Frobenius and keep track of your indices and so forth, and do a lot of work to find out the solution. Here, what you do is you pick the right kernel, and you want to make something that's analytic in Z and W, or even entire in Z and W with no singularities. You pick one, and then you will find that the V is very easy to find, such that the KV gives you U. And so then you'll have a formula for U, but of course the formula for U is no longer a simple power series, it's a contour integral. And so what you gain in finding V very easily, you lose in that your formula for U is a contour integral as opposed to a nice power series. So there's some things, it's all right. So let's see how this works. What we want is that L sub Z on U plus CU is vanished. That's what we want. And so what is L sub Z on this thing? Well, it's a contour integral of K of Z and W, V of W, dW, plus C, and this is the same thing, K, dW, V of W, dW, W a complex variable, of course. And so putting this together, assuming that the contour doesn't explicitly depend upon Z, then the derivatives here just act on K. And we have the contour integral L sub Z acting on K of Z and W times V of W plus CK of ZW V of W dW supposed to be 0. So that's what we want to solve. And okay, so what is the trick for solving this? Well, the trick for solving this is to find another differential operator, M, such that the M now is a differential operator involving W derivatives. So that M on K of Z and W is equal to L, which is a Z, which involves Z derivatives on K of Z and W. So this W doesn't mean we're differentiating M with respect to W. It means that M has W derivatives and L has Z derivatives. In fact, maybe what I should have written is this, is M of dW K of Z and W is equal to L of dZ of K of Z and W. Okay, so the second the work then is to figure out what M might be. And now, if MK is LK, then we can replace LZ K with MWK. And then we have that this is actually a contour integral of M, and let me write it maybe in this way, which is clearer. Okay, so now what we have is a contour integral in which we have a differential operator involving W derivatives acting on K times V, and C acting, C just the kernel itself, K. And so that's the, we're sort of halfway, 3/4 of the way through this. The next thing you can do, you see, though, since you've got a W integral and you've got something with W derivatives, you can integrate by parts. And when you integrate by parts, what you have is 0 is a contour integral of, after integrating by parts, you get, all right, let me write this as what it basically is. It will be K of Z and W, and then whatever happens when you integrate M, let me call this script M of dW acting on V of W plus C V of W dW equals 0. And now we see we have something very simple, namely all we need is 0 is M of dW acting on V of W minus K of D and W dW should vanish. So do I have this right? No, I've got it wrong. So it's, in other words, what we wind up with is a differential equation for V of W. Now you might say, this is this is bait and switch. In other words, we started with a differential equation for U. We went through all this trouble to find a K, then find an M, and we wind up with a another differential equation. Well, it turns out that one can arrange for this to be a trivial differential equation. So this one is easy. All right, there's a question there. Yeah?
I was just wondering, what did you do to get script in?
Oh, that's what happens when you integrate by parts.
Oh, you integrate by parts to get all the derivatives off of K and onto
You know, your candy stores are going to challenge Jeff Bezos pretty soon.
What is that?
He's the head of Amazon.
Oh, okay. Yeah.
His bachelor's degree, by the way, was in computer science.
C? C?
All right.
The letter C?
Yeah, I never see.
Oh,
I have
yeah.
a question.
Yeah.
Where is C?
What?
Where is C?
C. It should
Where
minus
is
C.
There isn't any Z anymore.
C.
C. When you go up
Third
to
letter
the
down.
easy differential.
Yeah, the Z has been,
No,
the C is effectively inert here.
C is in Charlie,
C?
as in Charlie.
C is just a constant.
Yeah, but
How
it's
we go?
gone. When your easy differential equation up there, you don't have it anymore.
It's a plus, right?
All right, what you're
What? Should it be plus? Yeah, should it be plus?
What?
Should it be stripped M differential on?
All right, so you're the one who asked, all right, there you go. Okay, what is the,
Well, he's asking why is it minus CVW? Why isn't it plus CVW?
all right, I screwed up. All right, I'm not giving a candy.
Okay.
Well, I can give one candy. Who suggested it?
Candy
That
store.
was him. No, I was trying out.
Who? Lee? Yee?
Yee.
About what?
Oh, you noticed that there was
All right,
no
do you want
plus
another
sign?
candy?
No.
All right, now, this business actually works really nicely. I mean, it's a useful technique because you can arrange for M to be very simple, and for this to be a very simple differential. And this is why, let me just give an example of some of these terms. U of z might be an integral from minus infinity to plus infinity, e to the I zw, v of w, dw. Well, this, of course, is a Fourier transform. If instead you say that u of z is an integral 0 to infinity, e to the minus zw, v of w dw, well, this is a Laplace transform. All right, now let's get to the Bessel functions. For the Bessel functions, the differential equation is z squared u double prime plus z u prime plus z squared u minus lambda squared u equals 0. The eigenvalue, in a sense, is squared there. So what's the differential operator else of z? It is z squared d2 dz squared plus z ddz plus z squared. So that's L. The constant c is minus lambda squared. And it turns out it's a very simple choice of m. Namely, m is minus d2 dw squared. Okay. So you can see the advantage of this hocus pocus. Yes?
Do we need to see what K looks like to see M?
I didn't understand.
What is K here? Yes, in this case. What is KZ omega?
What is K? Oh, yeah, you're right. All right, I didn't say what K was yet. All right, hold on. What you can, you see what you can do, or I've gotten things, in the derivation, or in my description of this process, I said, you've got you choose a K, you imagine a K, and if you're lucky, you can do all this. Well, it turns out that what you do is you are looking for a K that, for a simple M, solves this equation. Okay, that's actually what one does. In other words, you want something really simple, like M is minus d2 dw squared. If that's the case, find a K that does this. All right, so let's do that. M is minus d2 dw squared, and so what we want is mk is equal to lk. And mk would be minus d2 on k dw squared, and we want this to be lk. Well, lk is z squared k double prime plus zk prime plus z squared k, prime being d by dz. And so what's a k that satisfies this? Well, it turns out you can let k of z and w equal e to the plus or minus I z sine w. And so you can just verify, obviously, derivatives with respect to w, these things kick out a cosine, a plus or minus I z. In other words, k or dk dw is equal to plus or minus I z. In fact, it's actually minus or plus I z cosine w times k. And then if you do the second derivative, minus d2k dw squared is equal to, a little manipulation shows that's z squared sine squared omega times k plus or minus I z sine, no, minus or plus I z sine omega times k minus z squared k. And that you can rewrite as, well, anyway, you can see that a little manipulation, you can see that solves this equation. The result then is that we then can transform the equation into this form. Did I leave out a minus sign? Which was always on. All right, let's just see what we originally had here. We had LZ is MK.
I think when you put dk d omega, is it still plus or minus? It's like you made it minus or plus.
Yeah, I did that because there was an overall minus. Oh, you mean the dk dw?
Yeah.
Oh, that's because when you differentiate sine, you get minus. Oh, you're right, it is plus minus. It's sine, with respect, sine, I thought this was a cosine, that used a minus sign. So instead, you're absolutely right, it is that. I think this is right. Anyway, apart from, there may be a minus sign loose here that I'm just now noticing. But what one gets here is KWW of Z and W. This is the double W derivative. And it seems to me we should have a minus sign there. Plus lambda squared K V dW equals 0. And then we can integrate by parts, and when we integrate by parts, what we get, if we integrate once, we get KW V prime plus lambda squared KV plus, look, I'm going to follow what's in the notes. There may be a minus sign loose, but if I try to fix it on the fly.
Did we define m to be minus?
Yeah, I had a minus sign there.
There is a minus in C, in lambda squared.
Or look, I'm not sure whether this should be plus or minus.
Oh, yeah, because it's in there.
Okay, so that's the minus sign, the may not be, because I think the signs are probably correct in what I'm doing. Anyway, the next term is dKWV, dW, all that dW. So that's the contour integral of the W plane. You integrate once more by parts and you get K times V double prime plus lambda squared V plus d by dW of KW V minus K V prime. Prime means d by dW. K sub W means dW of K. So I could have written K prime. dW. Okay. The next thing is that you choose the contour to make these guys go to 0 by choice of contour C. What you then have, if you want the whole thing to be 0, you just have a very simple differential equation. And the simple differential equation is d double prime plus lambda V equals 0. Well, this is our harmonic oscillator equation. And so what is the final result? Let me get a piece of chalk that's sharp that you see. Let's see, I owe somebody a candy. Who is it? Who? Oh, right. Almost. Okay, so what one gets is this. U of Z is an integral on C, K of Z and W, B of W, and W. Now, B of W are the solutions of this equation, which is a harmonic oscillator equation. And so B of W is e to the I lambda W. And so this is then an integral. What is K? Well, K, I told you, was plus or minus IZ sine W. So this thing is e to the plus or minus IZ sine W, e to the I lambda W dW. So that's our solution for the Bessel function. And now you must choose a contour to make these guys go away in boundary terms. And there are various choices of contour that will do this. And I suspect, since we're talking about the general Bessel function equation here, that if you choose one contour, you get the ordinary cylindrical Bessel functions, the J's, and you choose another one, you get another solution. Or actually, no, I take that back. We're going to choose two contours that both make the boundary terms vanish. And these contours are going to be as follows. C1 runs from minus I infinity up to minus pi, goes over to 0, and then goes up to I infinity or plus pi. So this goes from minus I infinity, minus pi, sorry, up to I infinity, no pi there. That's C1. C2 runs from pi plus I infinity down to pi, so this one is going this way. This one is going down, goes over to 0, and then goes down to minus I infinity. So these are the two contours. Those two contours define the first and second Hankel functions. H lambda 1 of Zn is minus 1 over pi. Oh, well, inasmuch as, all right, let me just draw this. Integral C1 e to the minus Iz sine w plus I lambda w dw. Notice lambda is an arbitrary complex number here. So that's the first Hankel function. The second one is minus 1 over pi integral C2. Well, it's the same bloody formula, e to the minus Iz sine w plus I lambda w dw. So those are the two Hankel functions. This thing is an entire function of z and w, and so you can deform it. Let's see, I needed to say something about z. You need, in order for these boundary terms, can you move the camera a little bit? In order for these boundary terms to vanish, on these contours, you need a real part of z to be positive. However, the contours, once you define the functions in terms of these contour integrals for positive z, you can then notice that, well, this is we can change the value of z, and there's no singularity, and so what one does is one makes it, one can analytically continue the Hankel functions outside of the right half plane, this being the right half plane. And what one finds then is that H1 is H2 complex conjugate. So these are the Hankel functions, and the Bessel functions of the second kind are defined in terms of them. That is to say, one writes H1 lambda of z as j lambda of z plus I y lambda of z. And so these are the ones that are regular when z is small. These are the ones that are irregular when z is small. And similarly, H2 lambda of z is then j lambda of z minus I y lambda of z. And so this expresses j as basically the j lambda then is h1 plus h2 over 2, and y lambda is h1 minus h2 over 2I. So that defines the two kinds of Bessel functions. And the y's turn out to be irregular for small z. Okay, I guess that's more or less everything. So are there any questions now?
I have
An unrelated,
minutes
all right.
that so I was thinking, like,
Oh, here
Thank you.
is one of your candies also.
Okay.
Okay, so what's the question?
Okay, so on the space of even functions defined on the interval from minus pi to pi,
Space of even functions, even in x,
even in x,
from minus pi to
from
pi.
minus pi to pi, they can all be written in terms of a Fourier sine series, right?
I would call it Fourier cosine series.
Oh, sorry, no, I mean odd functions. I meant to say odd
All right,
functions.
odd functions, Fourier sine series.
Okay, sure. So you could get a formula.
Well, you didn't say periodic. I mean, you can do the sine series,
Sure.
whether it's periodic or not, between minus pi and pi. But
Yeah.
if the thing is not periodic, it's going to be a jumpy thing at minus pi and pi. You're going to have those
Sure.
things that's named after that guy, I forget, who was mistreated at Yale. What?
Okay, so the question, so because of that, you can get one of these nice little formulas for a delta function, right? And I would imagine that it would be some sum over like sine of n x, sine n y.
Well, but it'd be a delta function only good for odd functions.
Sure. Okay.
But normally we think of a delta function as something that's good for any function that's suitably smooth.
Sure. Sure. So, okay, but my question
So that would
is-
be a very odd delta function.
Okay, sure.
Get any laughter out of anybody.
Oh, yeah.
Yeah, I smile.
Odd functions. Yeah, okay, no, but, I don't know. Could I write something on the board?
Yes.
Sure, okay. So I don't know, I was thinking, okay, so if you could get a formula like this, like some number n of like sine in x, sine in y, equals maybe, I don't know, like 1 over 2 pi times the delta function of x minus y. I was thinking, what if you set x and y equal to 0? Then all terms here, or even if x is 0,
Yeah.
all terms here would be zeros. You know, 0 plus 0 plus 0. But then you would have sort of like a delta function at 0,
Yeah.
which sort of like
Yeah.
diverges.
Okay.
So I don't know. I was just thinking about that.
All right, well,
I wondered if you had any-
What you're saying can lead to something.
Okay.
Now, what I said was it would be a very odd delta function if it only worked for odd functions.
Yeah.
Okay. But the delta function, as you know, isn't really a function, it's a distribution, which is to say it's a linear map, a linear continuous map from the space of suitable functions into the real numbers or the complex numbers, depending on what distribution it is. So what you could define here would be, it would be a linear map from the space of odd functions into the numbers. And that would be a distribution of sorts. Now, what I don't know is whether when you define continuous linear functionals from spaces of functions into numbers, whether the spaces of functions have to have certain characteristics so as not to be, just odd functions.
Sure.
And in fact, the spaces of functions that people do talk about, these are the mathematicians, okay, white coats on the other side of Lomas. The spaces are always spaces such that they're super smooth, they go to 0 and infinity, and the advantage of being super smooth and going to 0 and infinity is you never have a problem with the boundary terms. You can integrate by parts and you never have a problem. But for example, one space that a Russian, this guy Gelfand, who later went to Rutgers when the Soviet Union collapsed, his space was the space of all infinitely differentiable functions that vanish outside of some compact set. In other words, they're infinitely differentiable on 0 to 1 and 0 everywhere else. And on the other hand, the French mathematician Schwartz You can't get away from the Schwarzes, there's always another Schwarz. Anyway, this particular Schwarz, in Laurent Schwarz in Paris, his functions were infinitely differentiable functions that, as you go to infinity, vanished faster than any inverse power of x. So they go down. I don't know if that means they have to decrease exponentially, but they have to go down faster than any, 1 over x to the 2n, say. By the way, I once heard a lecture by Schwarz in which, this was during the Vietnam War, actually, and he said, all right, I'm going to have to say something about something new that Nixon had just done, and he said, and then he spoke for 5 or 10 minutes against the Vietnam War, and then went on with his mathematics. All right, I think that's, any other questions?
Yeah, I was just wondering, so why is this the contour that makes that go to 0?
Why what?
Why is this these two the contours that make the boundaries?
Okay, I tell you what, that's a bit of a long story.
Oh, okay.
But what you can sort of see is, this is the W plane, right? So you have here sine of W, okay? And the sine of W then is e to the iw minus e to the minus iw. Well, if you put W equal to, say, I infinity, then this is e to the minus infinity minus e to the plus infinity, and this is in an exponential. Okay? So this is e to the 0 minus infinity, and that's 0. Okay? And then you can imagine that if you disturb this by adding plus or minus pi, that has no effect. And you can also imagine that if you do minus I infinity instead of plus I infinity, well then one is 0, the other one is infinite. And so anyway, it works. Okay, so you turned that off, I guess. Or?
No, I didn't.
All right, that's okay. So, but we're done? Okay, let's stop.